capacitance, our deal here is that we're still considering this two-plate situation here, but we also need to think about the area, and then this is going to be plus, we'll call that position 1, and then this will be position 2, right? So our charge, when we're dealing with capacitance, is equal to the integral of the area times rho ds, or sorry, this is P, not rho. PDS, where P is equal to the permittivity times the electric field, which usually I write this slightly differently so it's a little easier to figure out. So I usually write that P is equal to the permittivity using this E, just so I don't get confused in my notes, because it can be really easy to get confused. Now, if we put this into the same integral, this will become the integral of permittivity and electric field over some arc length, right? So ds. Now to deal with ds, that's when we're going to swap this to be just area. So now we have the integral of permittivity, electric field, area. Okay, and then we remember that voltage why is this relevant? Oh, okay, I see, I get it. Okay, so voltage is from 0.1 to 2 is equal to the negative integral of 0.2 and 0.1 of the electric field over some length, right? Which the quick and dirty of that, if we swap our bounds around, will just come out to be the electric field times the distance here, right? Because we already know the distance between 0.1 and 0.2, so the minus, so this is negative P1 minus P2, that is defined here as D, so that's why we're using D. Then E times D we already know, we're gonna use this up here to plug in for voltage. Because capacitance is defined as Q over V. That's where we're going here. So capacitance equals Q over V, which we now have solved here. So Q is permittivity, electric field, area, and V is electric field and distance between the plates, right? So now if we just do a little bit of quick algebra, we notice that electric field over electric field means that we just get permittivity, area, distance. We're given that E sub R is equal to 4, and we're also given that the area of this particular capacitor plate is 5 meters squared, which is massive, and the distance between the plates is 2 meters. So that's huge, that's humongous. So that's saying basically you have these giant plates that are probably like 1 meter by 1 meter, and they're 2 meters apart. That's huge, humongous. It's huge. Okay, so with that in mind, this becomes really just a straightforward plug-it-in problem. But do not get caught by thinking that ER is equal to E. It's not, right? We have to do E sub R, E sub 0 is equal to E. I need to be consistent with my E's, I'm sorry. Right? So E sub R is 4, and then E sub 0 is 8.854 times 10 to the negative 12th farads per meter. And then that's going to equal our E. And then we can plug that back in. Okay? So this is not a pretty number, so I'm actually just going to plug everything in all at once. So I can try and do this on a calculator, but I probably might still need one. Okay, 4 times 8.854 times 10 to the negative 12th. Okay, times the area we're given is 5, and then divided by 2. And then we know this is farads per meter, and then that's times meter squared over meter. So we're going to get something with farads, which is perfect because that's what capacitance is measured in. So we're doing good. This is really ugly, holy goodness. So basically we're getting, oh wait, no it's not, okay, yeah. 4 divided by 2 is 2 times 5 is 10. So we get 8.854 times 10 to the negative 12th times 10 farad, which equals just 8.854 0.54 times 10 to the negative 11th farad.